I will be using PTC Creo elements today to make a shoe, a dust shoe for my CNC machine, for which you see the model of the CNC machine here. I can move the Z-axis here in the CAD program by just taking the object and sliding it up and down along the Z-axis. I can also change that to move it along the Y-axis, as I will show now. Oh, actually I selected the wrong axis here. So I will show you how the dust shoe will look like when we have completed. It will contain several elements. Let me reset the view here for a moment. See, I'm having in the wrong orientation, so let's do that again. So we have 4 components that will form the dust shoe. And in this demonstration I will focus on the second item from the top. So here I already created the work planes, and I will extrude the actual part from these work planes. First I'll start with the outline, and I'll pull the outline to 15mm. A new part is being created. I will move that now in my container. I'll now extrude these black holes, which are going to be little holes in which I will put neodymium magnets that will help me attach the components together. And then I will apply a few like raised edges here, which will help me attach and secure the items together. I will also add the same magnet slots on the bottom, little magnet holes on the bottom, 5mm deep. I need to close this bottom part here, so I'll make a new work plane and take a projection out of the 3D components to make my initial geography that I can then extrude into the component itself to close this hole. I will make that like a 3mm thick. And this will close that hole. I will now change the sharp edges of the raised edges. Well, before I do that, I will change the detail level of the component to make the part more round. And then I will add the bevels on the raised edges. This will help me to easily attach the components together later when it's done. I still need to do the bottom slots. I will turn on the extension ring. The extension ring has raised edges as well, so I will impress those into the uh, part that I'm currently making, just basically by punching the holes into it. So that's now completed. And now the part is done, and I can export it as an STL file. This STL file will then be read in my CAM program, in which I will make the two parts. I will be using Kanban for that. I will show that later on in the video. We'll first export the STL file, and that's it. This is Kanban. I will open the STL file we created in the CAD package, and I will use this program to create the STL, the toolpaths from the STL files. Here I just imported the part. I now have to align this part closer to the center. Because this part has to be machined on both sides, I am making a copy of it, and I will rotate that part around the x-axis so that it can be machined on both sides. After rotation, I have to realign the height of the component of the part so that the z-axis is the same as the original part. So here I'm moving it back to z0. I'm creating a new layer. This layer will contain the masks that I will be using later for when I am making the machine operations. To make the actual masks, I select the part and do a plane slice. In this demonstration I select a plane size of 2 mm, which is very fine, but this is just for demonstration purposes. So here you can see all the polygons that are created by plane slicing it. Now I do not need all of these, so I will be deleting whatever I don't need, just by simply selecting the ones I do not need and then just deleting them. But this takes some time, so I will just skip this operation until the part is cleaned up. So here you see the cleaned out part, and this is the other side of the part. So we'll start with machining the bottom part of the part. So I created these two little circles here. These will be drill holes. I will use these drill holes to realign the part, the stock material. Since this part has to be machined on both sides of the stock, I will have to have a method so that I can rotate the stock around and realign the machine exactly so that I can machine both sides and the machine sides will align to form a single part when everything is done. I'm using a packing method to drill into the part. You can see that here. It goes in steps of 5mm down and then retracts all the way up. In this machine operation, I use these shape IDs as my margin. So this is my mask, these 4 items. And I will do a rough machining of the line to get the material out. So the depth increment is just 1mm, which is kind of rough for this operation because I want in the end to have a very soft sides. So 1mm would not be enough. But this is just to remove all these stock material from the middle of these parts. Depending on what you're doing, Kanban can take a very long time to actually generate the toolpaths. So after I created this, I will make the fine toolpaths, which only do the outside, or actually the inside part, the inside wall. So I'll select the same masks, and this time I will use a waterline finish method, and my depth increment is 0.2mm, which is much finer. So my stock surface here is 19mm, and I will machine up to a depth of 15mm. So here you can see the result of the second machine operation. These square holes these square holes here will be used later to be insert points for neodymium magnets that will hold the parts together. So I'm using different masks here. They are here highlighted. So I'm going by 4mm and my target depth is 13.5mm, and I'm using a 3.175mm V-carve bit here to do this. So this is going to be a very rough hole, and it will not actually give me a square corners. Because simply the bit is too big to create very square corners. To do that, I use a different machining operation with a much finer bit, 0.8mm, and I will go very slowly with this bit because this bit is so fine that if I would go any faster, I would break the bit in the machine. So here you see a very fine bit, 0.8mm. And we'll go in 2 steps. So here you see the machine operation. So the outer 2 lines are for the 0.8mm bit. So the top 2 machine operations are done with a 3.175mm ball operation. Balls. cutter. So I can select those two and then just do a top selection of the entire part and then generate the the G-code file in one operation. And then the drilling and the magnetic pockets are also using the same bit, so I can combine those and make a single G-code file. And this is the only operation that uses 0.8mm bit, so I just directly select it and then create the G-code file here. Now from experience I know that if I machine the part exactly to specifications, I will not be able to easily fit the parts together later. So what I'll do is I make another machine operation in which I do exactly the same operation as the roughing operation here, but I'm using the same bit, but I'm specifying a smaller bit diameter, so that will basically make the hole a bit bigger, and that will allow me to later align basically the two parts together very smoothly. So here I'm preparing the other side of the part. In here I will do a very rough cut of 6.35mm to remove most of the stock material. So I'm using these other shapes as my masks. So this is 123 for this part. So this is the rough cut of the top side of the part to remove most of the stock material that I don't need anymore. You notice that this middle part that I just pointed out will not be machined, so I will have to have a specific machine operation to remove that as well. So this is the inside part that I will rough machine out. Then this will machine the ridges in a nice smooth way. As you can see here. This is a very fine machining with a ball nose bit. I'm selecting these polygons as my masks for that operation. So these are the ones that were selected for that operation. I use this mask to specifically select where I want to machine so that I don't have to waste time actually waiting for my bit to machine everything of the part. I only want to machine these parts with this fine grade. So that's why the masking is very useful. Now these parts here that I'm just pointing out, these need to be additionally machined. So I created these square masks to machine these parts out. This is the other side. I have to machine this part as well. Then this again is for the magnet holes, again with a 3.175mm bit, 1/8 of an inch. And then I'll finalize that with again with a very fine bit, 0.8mm, with a very slow cutting again. And I have a cut width of 1.1mm here, so that will give me a very nice line. Final end result will be very nice. This part here is to make the smooth round end of the inside, so it steps down very smoothly so that I get this round transition from the hole into the slot. And then after that I will cut out the part. So this is the last machining operation. I will cut it down to -0.3 to make sure that I cut all the way through. I will cut into the spoiler board. I am also adding tabs so that you can see the tabs actually. So the tabs will keep the part fixed into the stock so that it will not slip while I'm still machining. I will then use a knife to actually break these tabs, and then I will send these tabs off the machine to part. So these are all the tool parts. So again, here I select the machine operations that I want to export into G-code. So this is the outside. I can just produce the G-code here. So the G-code will be used in the actual machine. I will using LinuxCNC to drive the machine. So I added a configuration in Kanban that will, when the machining is completed, will move my cutter to height 100 and position 00. I do that by, under system, go to the post processors and use the LinuxCNC one, and then select the footer part here, this one, and basically just add this in here. This will allow every G-code file generated to end with that. After you configure this, you save the settings so that it's in the system. This is the CNC machine that I designed and built. We're gonna cut the part out of 19mm thick poplar wood. Here it's cutting the first tool part with the 6.35mm bit, 1/4 inch bit. As you can see, a lot of debris is flying off, and that's one of the reasons that I'm building the dust shoe. So the first pass and the second pass with the same bit, I exported that as a single G-code file, and that allows me to immediately go from one cut into the next cut. So now it's currently milling out the raised edges in a rough manner. I'm cutting it in 4mm thick slices, so since the ridge edge is only 4mm thick, I only need one pass for this depth. This bit is big enough to do this in one pass with this speed without breaking the bit. And so after the first pass is done, it will immediately go to the second toolpath, as it is exported in a single G-code file. Because this part is deeper, I am going several passes, every pass at least 5mm thick. So we go in 3 steps. This is the end result of the first pass. I now loaded the 3.175mm ball nose bit, and this bit is going to make the round edges using several passes. Each pass is only 0.2mm deep. In the foreground you can still see the unrounded part, which will start now. Start cutting off the sides here and smoothing it out. But this takes time, so I sped up the playback of the video here. And this is now almost the last raised edge. You can see on the middle left side there's a raised edge there that I still have to cut out with a different toolbar. And here you see the y-axis of the machine driven by the stepper motor and the Z-axis. The spindle is water cooled. On the top you see the water reservoir with the embedded pump, and on the back side, invisible from this point, is the radiator, and this is the stepper motor for the Z-axis. And as you see, when it's finished, it goes to the 0 position. So depending on the bit that I use, the bit diameter will be different, so I'll use a different collet. So you can see two different collets here. I'm now loading out the smaller collet because we're gonna start using the 0.8mm bit. This one. You have to be very careful when loading the bit, because if you touch it with the tool, it will just snap off. So carefully tightening the nut here, and trying to zoom in here on the bit, but it's so tiny the camera doesn't really focus well on it. So this hole will be cut in two passes, each 2mm deep. So this is the first pass. You can see I'm moving very slowly because if I go too fast, the bit will just snap off. The cut is so fine that the material that comes out is almost like a powder. And you see the bit going down another 2.5mm for the next depth increment. So the spindle is spinning at 8000 RPM, which is controlled through the G-code, and then the LinuxCNC will drive my variable frequency drive directly to control the spindle. So I can program any speed I want in the Kanban program, and then when LinuxCNC executes the G-code, it will then drive the variable frequency drive to the correct speed. This will take a very long time, so I accelerated the playback here. And again finished. I can just vacuum off the dust, and you can now see the square holes. So the inside will be cut out with the 3.1mm bit. And this ridge here will also be taken out. So here I loaded that 3.175mm bit, 1/8 of an inch bit. And I'm starting to cut out that additional ridge here. Then in the center I also have an additional ridge that has to be taken off. So that's what's happening here. And this will be later smoothed down with another tool part. Now I'm drilling the center holes. This is not actual speed. I increased the playback of the video here. And now we end up with nice square holes in which we can fit the neodymium magnets later. And here I'm cutting out the part itself from the stock. So the stock will be holding the part with the tabs that we programmed in the Kanban. The tabs are only 3 mm high with a 3 mm base, and they are a triangle. That will make it easy to cut them with a knife later. So here's the part done. So I disconnected the stock from the table, and I'm flipping it over. As you can see, here's the back side already machined, and you can see the tabs which I'm now breaking with the knife. And after the part is taken out of the stock, I give it a light sanding, after which I will use a Dremel tool to take off the tabs. So here you can see the tab with a small triangle, which you can just take off with the Dremel tool. And this is the other part of the vacuum hose attachment. I'm machining the bottom holes, and now you can see that the machined part that we just finished machining fits nicely in here. It just snaps in place, just like that. And this is the other attachment, the brush attachment, which also fit into this one. This is the top part, then the machine part that snaps in here, a really tight fit, and then the brush with the magnets already in that attaches to it and then locks in place. So I will just slide this over the spindle, and then there will be a little screw in the wood that I can tighten up. And here's the total dust tube with all the rings on it, plus the vacuum hose, and going through some test motions here. You can disconnect just by pulling it off. You can see that it's very strong, connected with the magnets. You can take the additional ring out if I have a bit that is not as long as some of them. You can also take this part off for cleaning later. It just snaps into place.